In a previous learning objective, I mentioned elastic and inelastic collisions. This learning objective is all about that, specifically that you can describe the conditions for elastic and inelastic collisions and provide examples for each of them. Before we start this discussion of what is an elastic and what is an inelastic collision, we need to make sure one thing is very clear. All collisions conserve momentum. No matter what the collision is, all collisions conserve momentum. But elastic collisions conserve something extra. When a collision is elastic, that means it's like the perfect bounce. If you think of a bouncy ball where you drop it and it comes right back up to where it started, that would be the perfect bounce, and that would be an elastic collision. So elastic collisions, the most important thing you need to understand is that elastic collisions conserve kinetic energy. Now, we haven't talked about what is kinetic energy. Kinetic energy is 1/2 mv squared. M is the mass, v is the velocity. Kinetic energy can be described as the energy an object has because it is moving. So because it has a velocity, objects have energy. You can think, a train that is moving, does it have energy? Absolutely. Does it have a lot of energy? Well, it depends on how fast it's going. A train going 60 miles an hour, does that have a lot of energy? Absolutely, it has a lot of energy. Because the train has a large mass and its velocity is large, would mean the kinetic energy is super large. Now, what does it mean for kinetic energy to be conserved? That means, just like the conservation momentum law, that means the sum of all initial kinetic energies is equal to the sum of all final kinetic energies. So if we have two objects in the system, so let's take a look at the graphic to the right. We have object A and object B. They're both traveling at a velocity, and they both have a mass, which means they both have kinetic energy. If you added the kinetic energy of the object A and object B together, and then let them collide, and then measure their kinetic energies afterwards, the total would be the same. And we'll have an example where we do this. Before we move on, we should talk about kinetic energy is also a scalar quantity. Now, a scalar quantity means it does not have a direction. Kinetic energy is not direction dependent. In fact, all energy is not direction dependent. It doesn't matter which direction an object is going for its kinetic energy. And this kind of makes sense, because why would energy matter which direction you're going? A train has the same amount of energy whether it's going to the left or right. And negative energy just doesn't make sense here for kinetic energy. If it's moving at all, it's going to have some kinetic energy. Now, the advanced reason for this is because velocity is a vector. How do you square a vector? Well, you actually do something called a dot product. And what a dot product returns is a scalar quantity. So by taking velocity and dotting it with itself, you get a scalar quantity, which means kinetic energy will be scalar. And all you got to remember about scalar is that it does not depend on which direction. So you're not going to have a negative kinetic energy. So you also don't have to keep track of whether the object is going to the right or left to discuss whether it has or what its value of kinetic energy would be. Let's now contrast elastic collisions with inelastic collisions. Specifically, we're going to talk about the perfect inelastic collision. Technically, collisions fall on a spectrum. You have elastic collisions to inelastic collisions, and you have stuff in between. All collisions would happen somewhere in between perfectly elastic and perfectly inelastic. But we're going to talk about the perfectly inelastic case. For all cases of inelastic, total kinetic energy is not conserved. That's the important bit here. The amount of kinetic energy the system has is not going to remain the same. For a perfectly inelastic collision, objects stick together. So objects stick together in a perfectly inelastic collision, or they do not bounce, in other words. So this would be like if you dropped a ball of clay on the ground. The ball of clay does not bounce. The ball of clay hits the ground and splats and spreads out. That is a perfectly inelastic collision. And you can also have a perfectly inelastic collision, as represented with the infographic to the right, where the objects, when they hit, they stick together. So these two objects are, object A is coming in, it's going to hit object B, and then when they hit, object A sticks to object B, and now they're moving together as one group. That is a perfectly inelastic collision. Now, this velocity 0 here actually should not be the case. So let's go ahead and just get rid of that. It will have some velocity, because remember, all collisions, all of them conserve momentum. The total momentum is conserved no matter which type of collision we're talking about. It's just that elastic conserves kinetic, and inelastic does not. So that's the other point about inelastic collisions we need to talk about. Total kinetic energy is not conserved. What does that mean mathematically? That would mean that the sum of all kinetic energies before does not equal the sum of all kinetic energies final. So if you add up the kinetic energy of object A and the kinetic energy of object B, that's not going to equal the total kinetic energy after they collide. We'll get to where that energy goes later, because one very, very important law of physics that you should understand is that total energy is always conserved. But if kinetic energy is not conserved, where does that energy go? We'll talk about that in a bit. First, let's have an example of identifying an elastic or inelastic collisions using the math. The first thing we're going to do is we're going to start with this equation right here. The sum of all kinetic energies initial equal the sum of all kinetic energy final. But here you might notice I put a question mark, because what we're doing is we're going to plug in values to this equation and check whether they are actually equal. If we get some nonsensical answer like 5 equals 2, then we know that the kinetic energy was not conserved. But if we get 5 equals 5, then we know the kinetic energy was conserved. To start this, what we're going to do is we're going to take that sigma and we're going to break it into each individual object in our system. So what we did was we took that sigma and broke it into two objects. We have the kinetic energy of object A initially, plus the kinetic energy of object B initially. And we're going to set that equal to the kinetic energy of object A final, plus the kinetic energy of object B final. The next step would be taking this kinetic energy and rewriting it as 1/2 mass times velocity squared. This would be a great time to recognize any zeros. For example, if velocity of object A, I should say, was actually 0 to begin with, we could take this entire term and just make it 0. But in this case, none of these values are 0, which I should talk about this table. So what I have here, this table, is the mass of object A, the mass of object B, the initial velocity of A, the initial velocity of B, the final velocity of A, and the final velocity of B. So it's all the values that we're going to be plugging into this equation down here. One handy thing to do before you start plugging in values is we could notice that every single term in this equation starts with a 1/2. Every single term starts with a 1/2. If every single term in an entire equation has the same factor being something multiplied by it, we can eliminate that factor. Essentially what we're doing is factoring out the 1/2 on one side, and then we get 1/2, and then factoring out something on the other side, and we get 1/2. Essentially what we're doing is we're going to get 1/2 times some value, x. That's just whatever's left over, equals 1/2 times some value, y. And we notice that if 1/2 x equals 1/2 y, then x equals y. So we can get rid of the 1/2. Well, let's go ahead and just do that really quickly. What we're going to do is we're just going to get rid of the 1/2. It goes away. So let's rewrite this equation. Anytime we can simplify an equation by simply factoring out something or canceling something, you should always take the opportunity to do that. So now we're left with this equation where we have the mass of object A times the velocity of object A initial squared plus the mass of object B times the velocity of object B initially squared equals the mass of object A times the velocity of object A final squared plus the mass of object B times the velocity of object B final squared. Whew, quite a mouthful. Now what we're going to do is we're finally ready to start plugging in values. Okay, I just plugged in all the values from the table into the equation that we had. And I want to point out a couple things. The first is that we have this negative inside of the squared. I purposely did not square the number already because I wanted to show you what's happening here. So some of these velocities are negative because remember, velocity is a vector quantity. It can be negative or positive. But when you put a negative number into the velocity squared. You're squaring a negative number. And whenever you square a negative number, you're going to get a positive number as a result. This is another reason why you're never going to have a negative kinetic energy. Because if velocity squared is always positive, and mass is always positive, which it is, what would a negative mass even mean? That would make sense. Negative masses just don't exist in normal, everyday physics that we're going to be doing, and also do not exist in any physics that I'm aware of. Then if you take a positive number times a positive number, you're always going to get a positive number. Kinetic energy is always positive. All right, I'm going to go ahead and solve or evaluate this. Before I continue to solve or evaluate the rest of this expression, I should point out a couple things. First off is the units of kinetic energy are going to be kilograms times meters squared divided by seconds squared. Another way of writing this actually would be if you took the meters out, one factor of the meters, you get kilograms meters divided by seconds squared, which you should recognize as a Newton. So you also have a Newton times a meter is the units of energy. Also, this unit of newtons times a meter, or kilogram meter squared per second squared, has its own unit. So the unit of energy is a joule, capital J joule. The second thing I want to point out is the total kinetic energy of object A remained the same, even though they switched directions, which we talked about before. But what has changed is that the kinetic energy of object B is much less than the kinetic energy of object B originally. Its speed, the absolute value of its speed, only changed by 6 meters per second. But the kinetic energy difference is huge. So even though the velocity didn't change that much, there's a huge drastic change in the total kinetic energy. And the reason for this is because of the squared. Whenever you have a value that's being squared, it's going to be much more influential to the value of your expression. Whenever you square something, if it increased by 2, so actually, let's just take a little side note here. If you had x squared, and then you changed x to be 2x, so that 2x is inside the square, because what you did was you made x 2 times as large. Let's distribute that 2 in, and you get 2 squared times x squared, which is 4x. So whenever you multiply x by 2, you're going to quadruple the value of your end product. So whenever you have something being squared, cubed to the 4th power, whenever you have something to the higher powers, any small change in that value makes a huge change in the overall value of your expression. So we finished evaluating all of the numbers in the expression. And then what we get in the end is that the total kinetic energy initially was 3,060 joules. And what we get in the end is that the total kinetic energy is 660 joules. These two numbers are not equal to each other. And we could have noticed that because the object A's kinetic energy did not change. So if there's any change in object B's kinetic energy, then we're not going to have the same amount of kinetic energy before and after. Therefore, and we can use the triple dot notation to represent therefore, since these two numbers are not equal, therefore, this collision is inelastic. Since those two numbers are not equal to each other, this collision must be inelastic. Let's now answer the question that I brought up earlier. If kinetic energy is not conserved in inelastic collisions, where does that energy go? Let's take a collision of two objects. When these two balls collide together, they hit. And when they hit, you can think of billiard balls, you will hear a sound. You usually hear the sound of two billiard balls colliding. You might not realize it, but sound carries energy with it. Sound has energy. If you think of an incredibly loud sound, you could move an object with an incredibly loud sound. Think of a really, really, really loud set of speakers, and you put a piece of paper in front of it. That paper is going to move. And if that sound caused the paper to move, then that sound is giving energy to the paper, kinetic energy to the paper, which means that energy had to come from somewhere, so it came from the sound. So sound carries energy. So that's already one example of where energy is leaving the system of these two balls. Now, another one, maybe think in your head on a picture of two metal balls that hit each other really fast and hard. you might get some sparks that fly off these two objects. Those sparks are hot. That's what causes them to glow. They're little pieces of metal that have a lot of kinetic energy. Temperature, because temperature is average kinetic energy of particles. And when they fly off, you're taking some of that energy away from the system again. And lastly, let's talk about the fact that these two objects, when they collide, they might break or they might deform, bend. It takes energy to break an object, to bend an object. If you tried bending a piece of metal, it's hard. It takes effort. It takes energy. This is why the collision of two cars conserves total energy. Even though the cars were initially moving and then they're stopped, that energy went into the sound, went into heating up the cars, and it went into bending the metal of the cars. Also, let's take a closer look at this barrier right here, this border between the two objects as they collide. So when they collide, they're hitting each other. And that collision is going to cause the atoms on the edge to be moving faster. And then when they move faster, they're going to bump into other ones that start moving faster, and that energy is going to spread through the object. Particles moving faster is an increase in temperature. So the temperature of two objects, when they collide, are going to increase. You could actually see this. If you took two metal balls, two metal objects, and hit them repeatedly against each other, eventually they'll start warming up. Might not be noticeable at first, but they will start warming up if you just keep banging them together. So overall, the energy in a collision can go in many places. It can go in the sound waves, it can go into heating up the particles in the object, and it can go to deforming the object. So that is where the energy in a collision goes. All collisions, in reality, are going to be some form of inelastic collision. Usually never perfectly inelastic, but pretty darn close to perfectly inelastic in many cases. No collision is actually perfectly elastic, because that energy is going to go somewhere. You're always going to have maybe sound or deforming the object or heating it up. You're always going to have some kind of energy go into a different form. I'll leave you with some practice. The first practice is I want you to provide a real-life example of a collision that is almost perfectly elastic. Try to avoid ones that I've mentioned in this video. And I want you to justify your choice. Explain why that collision is almost perfectly elastic. Next question. You watch a super bouncy ball hit the ground and return exactly to where it started. What type of collision is this? And more importantly, why? The what type is easy, 50-50 shot. The justification is what I'm looking for. Why is it one type or another? Lastly, you hear a collision. What type of collision can it not be? Very simple. If you can hear the collision at all, what type of collision can it not be? And although I didn't originally write it there, why? Obviously, you're going to justify your answer.